Hey everybody, my name is Nikita Ivanov. I'm a founder and I'm a founder of GridGain project and I run the company behind it. So what we're going to be talking today about is in-memory big data. And I'm not going to bore you too much with a lot of talk. So what I usually do, if any of you have been to my presentations before, what I try to usually do is split it into parts, and this is going to be basically pretty uneven. So we're going to spend about 10-15 minutes talking about just the general topics about why we're talking about in-memory processing all of a sudden, why it's important, some facts, and we talk about a little bit about GridGain, just literally 2 slides and very quickly. And then I want to spend as much time as possible to really show you some live coding. You know, what I've learned, I've been in this presentation for quite some years, and the best way to convince a group of engineers that something actually is usable and simple and elegant is that show you something. So I don't have anything to do, I don't copy and paste anything. I start with the empty idea, coding all the way out. And you're going to see exactly what it takes in 5-10 minutes how you can build a simple MapReduce application, simple clustering applications. You're going to see all of that. So obviously I'm going to show you very simple examples. We don't have time to show something big enough. But hopefully you get a sense of how simple, elegant, and productive it can be. And this is a key takeaway point. If there's any one idea I want you to take back from this presentation is that it could be that distributed programming in general can be simple, elegant, and productive. And hopefully I can convince you by the end of this talk. So, let's talk about in-memory processing. It's a very interesting concept. It's interesting because all of you know we've been doing this for half a century, but there's some interesting facts that are kind of interesting facts that are really interesting in a light that in-memory processing became so hot today in the last maybe year or two, and is gaining a lot of traction. It's very interesting to say that, for example, Gartner, in the bottom of the slide, says that in-memory processing will have the same impact as a web in the cloud. Now, as much as I like to be in this, as much as I am in this business, I don't think it's entirely true in my opinion, but it tells you how much plenty of analysts believe in in-memory processing. Why? And think about this few facts, I just really try to condense them in one slide. Think about this, 64-bit CPU that you all have on your laptops here can address up to 16 exabytes of memory. So that's pretty much all the data we have in the world today. The single CPU can address all that space. So in fact, we practically solved any capacity problem and addressability of a memory or a data. Think about another stats. The disks today up to 10 million times slower than memory access. It's up to. If you compare slow memory with fast SSD, it will be less than that, but we're still talking about probably up to 1 million times. But still, the disk today is up to 10 million times slower, 10 million times slower than access to memory. Now, this gap is staggering on its own, but what I usually think about this gap is that it really enables a very different family of algorithms and approaches you can do. So we can do a lot of different things in memory or in memory processing that we cannot do when dealing with the disk-based systems. Not only speed-wise, it really enables a very different approaches. You don't have to look at GridGain, take a look at most of the modern Google projects, Dreamly, Percolator. All of them are based on in-memory processing. And it's not like Google engineers are smarter than everybody else. It's just when you keep a lot of data in memory and it's become your primary data source, you can do very different things that's simply unattainable in a disk-based system due to performance. Another interesting aspect is, think about this. We all have known this for many, many years, for decades. Why do you even do the in-memory processing? One of the reasons was price. 10 years ago, 5 years ago potentially, the price was fairly prohibitive. Today, the last maybe half decade, the RAM prices go the same route as the disk prices. They drop 30% every year and a half. Think about this. I've spoken to a couple of customers of ours, and they keep saying almost the same thing, that the disk-based storage today is relatively free for corporate environment. Think about this. Disk is actually free today. You know, how many of you guys have a terabyte of disk at home in the consumer electronics? Almost all of you. Think about it. A terabyte disk today costs about $100, plus minus. So today, corporate people talk about, you know, heat consumption, you know, power consumption, you know, cooling stuff, you know, place in a data center, but not the cost of the disk itself. So we're going to get this exactly the same point with memory in about literally maybe 3 to 5 years. The good thing about memory is that there's a lot less heat generation or physical space or anything like that. So memory is going to be a lot more effective than the disks. Gigabyte of memory costs today less than $1. I can give you an example. GridGain we just purchased in California a rack for our own internal testing. It's a 1 terabyte of RAM. Think about this, 1 terabyte of RAM is about 12 blades in the rack. It costs us about $40,000. Now, take a mental pause and think about this. 1 terabyte of RAM costs you about 3 salaries of a Silicon Valley engineer. That's it. And you have a terabyte of RAM, you can process quite a lot, believe me. Working set of terabyte data, it's not a lot, but it's not small by any stretch of imagination. I mean, if you multiply, let's say, by 5, you get 200K, you have a 5 terabyte working set, that's a significant amount of memory. You can process some significant business in it. And whenever you have something in memory, if you have the right software, all your responses under a second with something like GridGain. So you can take, I don't know, weeks of Twitter, the entire files, completely in memory, you know, less than maybe 100K, and have any type of, you know, query, any type of processing on this data, particularly under a second. Pretty cool stuff. Another interesting thing is having lots of cores on the CPUs really helps a lot, because think about this, like 15, 20 years ago, some companies could afford to buy a large amount of memory, right? What was the problem? You had one physical processing unit, one core. So no matter how much memory you have in the system, you're still bound by this non-parallelizable hardware. Today you have, you know, 8, 16, 24, 48 cores on the system, and those are independent hardware processing units. So you can actually very effectively process those terabytes of RAM or gigabytes of RAM that you have in a single box very, very effectively. That's actually a very interesting point, and the Gartner analysts, most people think this is one of the biggest ones. Because, yes, you can buy, if you have money, a lot of memory, but if you have just one pipeline processing, you're basically not doing it in any way effectively. And today, we can do that. Now, those are just the facts, right? It's what happened. Why are we talking about in memory, right? Why is it? Because, for obvious reasons, the speed matters. I mean, raise your hands if for your business speed doesn't matter. I mean, even if it doesn't, if it's not a number one concern, speed matters, believe me. And today, with the 24/7 data streams, with everybody expecting anything right now, when I press the button, you know, speed matters. And a couple of facts. CITI says that on the Forex trading, anybody in financial will attend to that, a 1/10 of a second delay in the Forex trade costs about $1 million. And that's not a even more glaring statistic. Google says that a half a second delay on the query results costs them 20% of the traffic. So if you know anything about Google, traffic is revenue. Google's revenue is billions. 20% of the traffic is billions. So half a second delay on the query result costs them literally, you know, billions of dollars. So speed matters, and not everybody works for Google or Citi, but you can always kind of you can always kind of zoom in and zoom out this statistic to your own businesses, and you can clearly see how it affects you. You know, we see these customers literally on a daily basis. They come to us and say, let me give you an anecdote actually. We had a customer about 4 years ago that came to us and said, hey, we have a report that takes 30 seconds. It's really very basic. It's a Java program. It goes to Oracle database, crunches the numbers, and prints out the charts. Simple. It's a hedge fund, it's a private website. 30 seconds, right? They ask us, how do we make it like, you know, so we can put it online? Nobody's going to press the button and wait half a minute. So how long is it going to wait? Let's say, I don't know, 5 seconds, right? 5 seconds kind of most. So how do you make something 6 times faster? Think about this. How do you make something 6 times faster? So we looked at everything, believe me. We looked at the bigger box. We looked at the collocating Oracle with application. We looked at, you know, networks, you know, new CPUs, a lot more memory. Yes, Some of this can give you twice as fast, maybe sometimes three times as fast. Nothing would have given you anything, 6 times faster. Even this benign, cheapo problem. And we solve this problem by moving a lot of stuff in memory and parallelizing it, which is exactly what it is. And we actually got about 8 times faster on about full buses. So that gives you an example that you don't have to have a NASA problem or DoD problem or anything like that to actually hit the wall. And have literally no other ways to solve it other than actually putting stuff in memory as much as you can, or as much as feasible, and doing parallelization of this. Okay, so what is GridGain, and why are we talking about GridGain? So GridGain is, what we believe is a scalable in-memory data platform. We help you solve these types of problems. We help you move your processing into the memory. Technologically, there are basically 2 key technologies that I'm going to demo today as much as I can. It's compute grid, essentially in-memory compute grid, and memory data grid. And I have a slide about them down the road. Sometimes we can rephrase compute grid as a MapReduce or streaming MapReduce. Those are pretty much the same concepts with a different name. Complex event processing, CEP, is another concept that is kind of similar to compute grid. In-memory data grid is basically the ability to store data in partition fashion over a large number of computers, and we'll talk about it a little bit later. So the focus for GridGain is really, processing and storing terabytes of data in memory and hundreds of thousands of nodes, and really giving you as much as possible real-time response. So we do have stats and examples where we can store terabytes of data. Usually I work in sets in the low teens of terabytes, sometimes even less. You can store that in hundreds of nodes and get robust performance for any type of, well, I wouldn't say any, but for most type of query processing under a second. So we are this proverbial engine that gives you the ability to take terabytes of data, and that's a scale we usually work in, and get a sub-second perceptual real-time responsiveness. We keep talking about GridGain as something that gives you in-memory speed and database reliability. And in-memory speed means we work in memory primarily. Database reliability, unless or unlike many NoSQL storages, we are full transactional store. You can move money with us. You can build financial system without any worry. We're as robust as Oracle database, or any other database you can imagine. We support full asset transactions with two-phase commit protocol. Lots of optimization of performance, so we don't suffer because of that. We have native cloud. We have actually Java-based product, obviously. We have native APIs for Java, Scala, and Ruby. I'm going to show you Scala DSL today and how you can interact with Scala with GridGain. When it comes to clients, something that accesses GridGain from outside, we support practically every ecosystem. We support C++, .NET, and even iOS and Android, PHP, and REST, and the Memcached if you need to do that. One of the core technology we have is distributed in-memory object store. So we're not a columnar database. We don't have that limitations. We're a pure object store in memory. So you don't have to constantly, convert stuff from JSON back to object presentation, back and forth. We allow you to store exactly the objects you're dealing with in the application. So it has its own pluses, its own minuses, if you will, but that's what we did. So I have one extra slide just to talk a little bit about in-memory, compute grid and data grid, and we'll switch to live coding, so bear with me for another minute. So this is the technology that are very core to GridGain. I want to basically just stop by for a second and describe it. Compute grids on the left side. What is a compute grid? It's very simple. Just bear with me. If you have a task, it takes a long time, and you have, let's say, 3 computers in front of you, you can split this task into 3 subtasks, ship those subtasks to those computers, execute them in parallel, get the results back and navigate. In ideal use case, in ideal case, you get your task in 1/3 of the time. That's it. There's nothing more to it than that. That's the whole essence of a parallel processing compute grid, generalized MapReduce processing, any type of name you can attach to it. That's all there is to it. Obviously, every product brings a huge amount of details and specifics of this process, and we also do, but in a nutshell, that's it. Data grids solve a similar problem, but slightly in a different context. While compute grids solve the problem, how do I parallelize processing, data grids solves the issue, how do I parallelize data storage? Again, let's say I have a terabyte of data. but you only have, a bunch of computers where each one of them has, 20 gigabyte of RAM. How do you store it? Well, you have to partition, right? There's no other way. You have to partition data and store chunks of it on each computer. Once you do that, you open a whole can of worms. How do you transact? How do you query? How do you maintain? It's like a gazillion amount of issues. As a matter of fact, number of issues is facing the data is a lot more than the computer. It's a more complex system and ecosystem. So data grids solve this type of issues. What people usually ask me, what is the difference between a data grid and a data in-memory database and a SQL storage? We're not going to go with this route because the whole presentation could probably be about the differences. One of the bigger ones is that in-memory data grids usually provide transactionality. Not eventual transactionality, but actually ACID transactions. Without loss of much of performance. So what are you getting with eventual consistency? You're getting quick writes, right? You're losing reads most of the time, but you get quick writes because you don't have to be in transactional context when you do writes and eventual consistent transactions. So the full transactional systems, they may not have one-to-one speed in writes. They're going to be a lot quicker on reads, by the way. On the writes, they can be as fast as eventual consistency or slightly slower, but they give you the full transactionality. So you can move money, you can move accounts, you can do a lot of things that you cannot do with eventual consistent systems. So that's the bigger difference. And then there's a gazillion of others. We object store some of the other systems are columnar, some of the other systems like a document oriented like Mongoose and stuff like that. So we're an object store, we're a full transaction store. Performance-wise, benchmarks are usually a black art. We can do any kind of benchmark against anybody, but usually the numbers we give away. We do about if I'm not mistaken, we do about 800 reads per physical core, 800,000 reads, I'm sorry, of course. And we do about, I think, 100,000 writes per physical core on writes. So those numbers pretty much on top of that. So if you multiply by number of cores you have in the system, so we're in the millions of reads per second. And we're up to the million writes per second on a typical blade, if you will. So those numbers are very, and I'm talking about the partition cache, so I'm not talking about something up local execution. So our numbers basically wants to beat. We stack up pretty well against everybody in the space. All right, so what I'm going to do now, I'm going to switch to idea and start putting away. By the way, if you have any questions, we have a small group, just ask. Don't wait till the end. We don't need to have the whole Q&A. Just, what I'm doing, just ask me through it. We're going to start very simple. Again, I don't have anything to reveal, so you guys, follow me. I'm pretty jet lagged, so if I have any issues, you can help me out. So let me just check first whether we have enough resolution on this thing so I can actually see something. Yeah, let me just start, so I have an idea. So let me just basically create a class first and let's call something like this. And we don't need to see much of it. So by the way, since we're going to be doing some distributed programming, we have to have a grid cloud inside of it, on this laptop or somehow. So what I'm going to do, I'm going to create a small ad hoc grid right in front of you, just in this laptop, so we can actually run some interesting stuff. So I'm going to have 2 external nodes. I'm going to start from command line, and I'm going to start a 3rd node from idea constantly. So every time we run application, we're going to have a grid of 3 nodes, 1 from idea, 2 external, and we're going to see some interactions there. So with GridGain, it's very simple. If you download GridGain, we have something here going on, so let me just kill this. So yeah, so basically, if you download GridGain, you can go to the your downloads folder and simply do that. We have a bunch of scripts there, and just say you start, and let's see, it's just pass configuration. So I'm going to use print cache for now. So it's going to start right now. By the way, I don't have network on this laptop, as you can see over here. So it's fine enough for GridGain. You don't even have to have a network to run something on your laptop. I mean, the whole grid or micro cloud, if you will. So I'm going to start 2nd node in exactly the same way. I don't have to change any configuration whatsoever. We're big fans of basically stop working out of the box. Like if you guys use, Ruby on Rails, everything just works out, right? So configuration is actually if you need. Same with us. With GridGain, we download, you up and running in a second. in your small private cloud, private grid. So again, configuration full file is this. That's better. So I'm running my DevOps console in the background. So if you look at the dashboard, fortunately, we cannot see much because of the resolution, but you can see there's 2 nodes over here. We just started. You can double click on them and see a lot of configurations, for the nodes and everything else. So we're not going to spend too much in the console because it's barely visible here, but we're going to consult it from time to time. So anyways, we got 2 nodes running, and they obviously discovered each other. If you look at the topology snapshot, let me just find this out. Just switch to this node. There are 2 nodes over here. We have 8 cores because it's the same laptop, and so basically they see each other. And let's switch back to the idea of writing code. Let me ask you a question. How many of you guys know how do you start, let's say, multiple GBoss instances on the same computer? Or multiple WebLogic or whatever you guys use, Tomcat. So you can do that, right? You can grab port 8080 everywhere, create a secret configuration, change it to 8081 and start, right? Let me ask you a question. How many of you guys know how to start multiple GBoss on the same VM? Multiple WebLogic on the same VM. I don't know about JBoss, but I work for PA Systems. I know you cannot start WebLogic on the same VM, period. And that's a bit of a shame because obviously it creates the easiest debugging for you. If you can start the entire microcloud on the same VM, you can put breakpoints in different nodes and debug it all. That's exactly what GridGain allows you to do. So you can start as many nodes as you like in a single VM, let alone a single computer. That's given. So you can start as many nodes in a single VM. So what we usually do when we're debugging our algorithms, we start the whole GridGain and the whole microcloud in the VM. And we put the breakpoints everywhere we need to debug our distributed algorithms this way. Obviously, when you move it to different computers or different physical nodes, everything continues to work the same way. So you don't have any shortcuts. Your debugging is pretty constant. It's pretty cool stuff. So anyways, let's write something here very quick. So let's put imports, and those are pretty self-explanatory for everybody. Let me just get this stuff out of the way. A couple more. So Scala is the name of our DSL, and we need to get all this implicits out, and let me just do another one that I will be using. So to start a node from idea, let's look how it's simple to actually start a node that will join the grid and become a third node when you run something. It's very simple. We have a new keyword called Scala. You pass the configuration. Let's see what configuration we're using. If we go here, we're using the dashboard says example config string XML. Exactly the same thing here. And let's say anything we do inside of these brackets, under this body, essentially, will be executed in the context of a node that actually joined the grid. So for now, we're not going to do anything. It's just say print. So we're going to print out locally, and nothing else will happen. So let's say Scalathon. Not fun. So let's run this. And do this right. And it finally works, huh? And so we can actually use this. So when we run this, we're going to see exactly the same output, right? Nothing's going to interesting happen for a split. Oops. Let's see what happened. So we got 3 nodes, right? All right. Who's going to help me debug this? Yeah, I think we have networking issues. Hold on a second. So we're looking at the same nodes. So let's check the configuration. So we're talking the same configuration. So config file is example spring cache over here. Let's see over here. Yeah. Let's check the rest of it. That's actually coming down and see if we can actually start a node. Yeah, the node starts. Okay, so let me do something else here. So how about this? Let me just do some execution and see if that's going to work. So what we're going to do is, essentially what I'm going to try to do is to run the broadcast. So on a grid, by the way, ignore this $ sign in the end. For now, it's just a temporary for us in the DSL because we have the same names in Java. So not to avoid the confusion, we have the $ sign to the end of it. To the same edits that actually have the same name in Java API. They don't conflict with Java expansions of the name, so don't worry about it. But what we're going to do basically here is that we're going to basically run this closure, the print line and all the nodes. And let's see if it works actually. Because I think we're hitting some issue with these nodes. But let's give it a shot. I'm actually checking configuration for now. So I have GridGain home. Everything's fine. So let's give it a shot. See if it works. Yeah. So we had some glitch in the beginning. It would be interesting to know what was it. But anyways, so that works. Now check this out. This guy printed hello Scalathon, right? This guy printed hello Scalathon. So basically, successfully, broadcasted the message. Well, not the message, the closure, right? Now this is a very simple example, right? It's very trivial. It's like Atom on steroids. Nothing interesting. We're gonna get something more than that. But let me ask you a question. Did anybody see me deploy anything? Did anybody see any ends? Any Maven, SBT, anything, right? So these two nodes on the command line came in the middle of Siberia. I don't care where they are, right? How the hell did they know that a particular closure was sent to them and it was executed? Now check this out. I can actually change this. I can say, GridGain. I can change whatever I want to change and just click to run again. I don't deploy anything. I don't do anything. It's just keep on running. So I got the new output here. So it's a typical closure that I can put any code into it, right? So that's one of the coolest things about GridGain is our zero deployment, I would say, technology. So when you're developing with GridGain, especially distributed applications, you don't have to deploy anything. That's one of the biggest developer productivity boosts you can get. I mean, in fact, how many of you guys have worked in distributed systems like Globus, MDI, Data Synapse? Yeah. You probably know that the biggest challenge, the biggest time drain is when you're constantly deploying something. You change a line of code, you have to rebuild, you have to start, restart, FTP crap out, wait until it'll be deployed. So that's what usually, when I worked in Globus like a decade ago, that was the biggest challenge. I changed a line of code, I could go to lunch before it really gets kind of, properly redeployed. So with GridGain, this is exactly how you work. This is exactly how we work internally. That's most of our clients work this way. You can be as complex as possible. You can, create very complex closure execution, map reduce task, anything you want. And it just works this way. You don't have to deploy anything. So on the background, obviously, there's no magic here, right? So how does it work? It works very simply. So all this, a scout itself get eventually translated into the task. So through the whole sequence of implicits, right? We translate this closure with the broadcast as a complex map reduce task. So we basically have a compiler that translates the DSL, so to speak, into the MapReduce task. The MapReduce task travels to remote, remote, so hey, I don't have a class such and such, right? Who has it on that version? Because obviously we support versioning and everything else. So go back to original node and say, hey, can you give me the class definition for that particular task? It gives class definition, it marks this with the version, stores locally, and as long as you have this class task running, it's going to keep this class definition. Now the biggest challenge, obviously, is to maintain proper class loader structure. If you guys know anything about class loading, class loading structure can be extremely complex. Like in JBoss, there's a whole tree, very deep tree of class loaders, and we have to maintain exactly the same tree on every node. So that's not a trivial task. If you look at the source code, actually it's part of the open source edition. You're going to see a dramatic amount of code to actually maintain that properly. Because class loading can be very handy. So anyways, let's continue the example. Let's do something actually at least not as trivial as this one. Let's create the first simple MapReduce task. So it's going to run exactly the same way as the previous one. I'm going to comment this one out. So what I'm going to do is I'm going to use a spread now, and over here I'm going to basically the example I want to give you is a very typical traditional hello world example of distributed system. So what I'm going to do is I have a string. I'm going to separate the string into individual words and let every node print the individual word. Simple as that. So let's create a string. Just copy this one over here. And let's say we're going to split it by spaces. And we're going to yield a simple folder that prints out that. So that's graph. And now we have 3 nodes, 4 words. Somebody will print 2 words, but most nodes will print just 1 word. So you have this guy, it's part of the topology. So I print out 2 words, and so this guy printed GridGain, and this guy printed Scalathon, right? So everything works. Now take a look at how simple is that and how functional it is, right? Again, it's a very simple, trivial example. We'll get more than that. But think about this, how trivial is this? That's all there is to it. To simply have a very simplistic MapReduce. Now, it's not a full MapReduce. What's missing, right? What is missing here? Is the reduction, right? So, and by the way, if you guys are familiar with Hadoop MapReduce, the concept in GridGain is a little bit more advanced. In Hadoop, you constantly dealing with tuples, right? Tuples in, tuples out. And you have 2 phases, map and reduction. So with GridGain, we have a lot more higher order MapReduce implementation. You're dealing with actual code. You don't have to constantly convert your thinking, from code and objects to tuples, which are basically in the file, and those are strings in text. So it's a lot more convenient to deal with this way. So let's actually create something that is reminiscent of actual MapReduce. So we're going to create a function that calculates calculates, for example, a non-space characters. So let's pass a string, and it's going to return int. And it's very simple. So we're going to use the same grid, but now we're going to basically do reduce. And we're going to have 1 extra parameter with a spread. So what is spread in broadcast? Broadcast is broadcast, right? You get closure to every node. Spread means you're trying to load balance. So if you have 10 closures and 5 nodes, every node will get 2 closures. Again, you can control every single way here with actually, I'm showing right now something that's very simple, so don't get confused by this. All right, the closure generation, basically, step is very similar. We just, get words out. And we just yield them a little bit differently. We yield the name to length, right? Because that's what we calculate. And let's either add a reduction step. That's pretty simple, so we get sequence of int. And we'll do some issue. That's all we have to do. So if I comment this one out, and I'm going to say that a non-white space count is, and that's it. Now, what we're going to do is, so let's add some printouts so actually we know what's happening. So when we calculate the lengths, I'm going to basically add a phrase that we calculating for these, right? And when we do the reduction step, I'm going to add that we are reducing S. And again, as everything in GridGain, you change the code quite dramatically, just run it. All right, so let's take a look at nodes. So this guy was calculated for Scalathon. This guy was calculated for GridGain. The idea node was calculated for 2012, and for Howdy, it was also aggregating the list back, and the result was 26. Now, this is pretty close to actual MapReduce. I mean, it is actually MapReduce. It's fairly simplistic, right? You can obviously replace the length function with whatever you want to in summation with any other reduction step. But take a look how simple and trivial it is. And again, obviously, don't confuse simplicity with the depth of API we have. So I'm showing you a very simple thing. But surprisingly enough, in a lot of our use cases in Scala in production, the customers that we actually use this in production, is very reminiscent of that. Because you can always break down your problem to very simplistic steps, right? Let's say I have a complex option calculation or something like this. It can be done literally in this way. I mean, you can probably deal with a little bit more different topology. It will give you the ability to have very dynamic topology and projection, very functional, by the way, in our API. So let me just show you some of the things you can do. For example, over here, you can say, you know what, I want to do only remote projection. So you can do something like this. And then I want to name this task. Let's say I want to name it MapReduce. And if you run this again, what's going to happen is that this whole task will be executed only in the remote nodes, not on local. And we're going to see this task in our DevOps console with the proper name. So as you can see, there's no calculation here, only reduction. Reduction always happens on this node that initiated task. And all the calculations happen over here, right? And over here. So that's how simple you control. And obviously, the projection is very functional in nature. You can pass a predicate, you can pass anything, and there can be very dynamic. So every time you call it, it can be very different projection. It can be time-based, statistics-based, load-based, whatever. Simple predicate, the passing predicate, whatever's in the predicate, you can work with it. So if you look at the compute grade DevOps console, we'll all of a sudden see a new task that has a much better name than just a Scala contractions. And we can see a lot of statistics here, execution rates, max nodes, how long it took. And if we have a little bit better resolution, you can click on this task, you can see all different execution paths for this task too. So you can see which node, the start time, end time, the durations for particular execution of this task, and so on and so forth. So quite a lot of information here. I don't want to, spend too much time right now on this. So this is actually a pretty good example. Now let's advance the story. So we talk a lot about a failover, right, in the system. So it's hard to show it, but I'll give you the one example how it can be easily shown. So let's put this thing in a while loop. And just to make sure we don't crash the system, let's put some thread sleep here. Let's say half a second. And start again. So what's going to happen, we're going to keep on calculating the same thing in the loop, right? Let me show you some of the extreme cases of so here we go, right? If you look over here, the number of executions will just grow. We have update every 3 seconds. So 43, it keeps on going, So let me show you what we do. You see the node, right? It's running. I just click Ctrl-C to this. This guy just automatically pick up the load for processing without me doing anything. Now check out, we didn't change the code or anything. This is basically we're just doing this in a loop indefinitely, and this is the logic. We didn't do any explicit failover, nothing at all, right? So this node was killed, this node continued to go. Now, if I just start this node again, let's see what's going to happen. So it starts up and it picks up the load right away. So nothing to do, automatically fails over and does everything for you. It's pretty cool stuff. So if I kill them both, the task will actually fail because we say remote projection will be no nodes in remote projection. If I would have no projection, I could kill those two, and it's still going to run an idea because idea node is just as any node. Let's see. By the way, in GridGain, we don't have a notion of a server and a client or master or worker. We have completely peer-to-peer technology. So we have only one node. It's not a server, it's not a client. You can be anything, what do you want, in any particular context, any particular given time. So every node can submit tasks, every node can participate. You control the topology. So you can have a logical server, a logical worker. You can have a logical master if you need to. But most of the time, I found that that's very limited if you have one.
I have more questions about EC2 and Z-based stuff for later, but so this, you have mechanisms in place for auto scaling, like based on traffic on.
Yeah,
that's
you guys,
automatically-
we've had this previously, and then we kind of backed away because it's always very different how you can, for example, start multiple nodes based on some load. We actually have an idea, but we found that, for example, anybody from the market and the chef, and being an external solution can do just a better job, but not just a good job as we do. So yes, you can start extra nodes either from.
Well, I don't mean like necessarily having GridGain do that, but there's alarms that like
Oh, yeah,
electric alarms
sure.
built in that I can trigger my job. to
Exactly.
spin up
Yeah,
nodes.
it could be as simple like, if even the DevOps console right in this board, you have a start. And we use SSH to very complex starting procedure. You can start 20 nodes on 20 different machines with live configuration. So right from this dialog. So we have that, kind of manual operational support if you need to. Some people can actually use GridGain API to start a GridGain node from a GridGain. That requires, a little bit of code, 10 lines of code to start something based on whatever. So, but we had a lot more support in before with that, and what we find is a lot of our customers use external solutions for that. They monitor the systems, because sometimes it's not only about GridGain, it's about how your database is from, what's the load on this, what's the load on that, what's my file system capacity, how's my Hadoop do, do I need to start extra processing for the Hadoop cluster. So, we basically have some support, but usually people find that, they can do it from outside as well. I have about 5 minutes. Let me actually show you because what I'm showing you today so far was just a computer, right? There's nothing to do with data grid. Let me show you very quickly how you can actually do something to do with a data grid. And keep in mind, one of the key features about data grid is ability to decollocate. That's like a prime basic example, right? Let's imagine you have a data partition in a data grid, hundreds of nodes, each one has 100 of your data set, right? For any system to be effective for processing data, you have to collocate, it's called affinity collocation. That's like a one-on-one to your program. Because imagine this, if you don't collocate, let's say you send a job to a node that doesn't have a data, and the data is over here. Imagine what's going to happen. You have to move the data from this node to this node, serialization, marshal, and demarshal. Then you process something, then this data is completely unusable here, and you have to drop it in the garbage collection. It's a garbage collection spot. So, and in plain English, it's going to kill your system right away. So the collocation is a must. You don't have a single system that's not collocated in production today. It's, what I keep saying, you walk in the eBay office in the systems group, they have a huge banner like in half of this wall saying if you don't collocate, you don't scale. Like in eBay, you cannot even get to testing for production if you're not 100% collocated. Nothing's going to scale. So collocation is a must. We have to support that, and many other products as well. We have very cool support for that. Very simple. I'm going to show you right now. So what we're going to do, we're going to add like a 20 values in the data grid, and we're going to create we're going to collocate closure with each key, and we'll show you how simple it can be done. So let's get started. So we're going to have about, let's say, how many keys want to do? Let's say 20. Let's create a type so we can do quick something. Let's go cache. We're going to store ints. Key is going to be ints, and values going to be strings. So let me remove some of that so it doesn't get crowded because we don't see much here. So let's create 2 methods. One's going to populate the data into the grid, and into the data grid, and another one will visit. And visiting is going to be collocated, so we will know that. So population is pretty simple. Let's create the variable C. Go something like this, and we have a one partition cache. It's most interesting. We support 3 types of caches: fully replicated cache with small data sets, when it's fully replicated, massive read performance, writes is slower because you replicate. Partition cache is what everybody is using practically. It's a vector consistently based. It's partition cache, partition sharding, any terms you're using. And we also have local caches, basically just work as a local caches for. So we're going to use partition cache, one of the most interesting one. So the population is pretty simple, from 0 until none for each key. What we're going to do is something like this. It's a data string. files, desk. So the visiting is a little bit different, same from the same key. So for each key now, let's say when we call it populate, we're going to put 20 keys in a data grid, right? And look how simple it is. Our data grid, with all of its complexity, believe me, it's a fairly big beast. The only data path is pretty simple, like a map. So for you locally, when you when you're on the node, it's a map. You add, remove, and then there's like about 20 other methods you have. All the lock, sync operations. But in most cases, when you're dealing with this, when you're adding stuff to it, that's as simple as that. You just add a key value, as you do in map and Scalathon. So how do we visit this? So again, for each key, and what we're going to do here is that we're going to go we're going to call it feed around. I forgot the APIs here. So a feed around requires a name of the cache, so it knows actually what cache we're dealing with. It's partition cache. It requires the key. What are we collocating with, right? So we're saying, hey, take this cache, take this key, and take this closure, and collocate it on the same node where this key is stored. Value for this key is stored. And let's say what we're going to do here is that we're going to say print line, and we're going to say, well, the key is key, and the value. So now this is what's going to be a little bit of a trick. How do we know we collocated? Think about this. The only way to know is to run some very local operation that only deal with the data on that particular node. And if data is there, we get a null value. So we have an operation like that. It's called peek. So the peek actually doesn't do any distribution. What it does, it looks on the value on the local node. So if you collocate it, this value is going to be there. And the peek is extremely fast operation. No transaction, nothing. Just basically looks at the value on a particular node. If it's there, it turns it. So what we should basically get is that if we collocate properly, we should get absolutely no nulls anywhere, because we collocate everything properly. The peek is a local operation. That's it. So let's call these two guys. Populate first, and then visit second.
Partition. Is this spelling error on line 24?
That is not good. Let me see if we have the same name on the cache. This resolution is killing me. I cannot see. How do I see it elsewhere? I see it here. I'm on to router. Yes, full partition. Go. By the way, we support a full SQL API to our database or in-memory data grid, so we're going to show it to you. So once we put the stuff into this, we can use normal SQL. We actually support the DBC driver. We're shipping the DBC driver with our system, so we want to use DBC for querying and seeing what's inside your memory. Full SQL. We don't support like a great table or great index and not specific, but it's a SQL. Joins work if you have proper collocation. If you don't have proper collocation, you get multiple results back. So that's typical. Say, for example, your snowflakes, a star schema, joins can work perfectly fine. But I'll show you in a second. So let's run this first. So what we've got is we got 20 keys, so they got evenly split out somehow. So we got no nulls here, so everything's perfectly collocated here. Everything's perfectly collocated here, and here as well. So since it's basically it's consistent hashing, we don't get like a direct split, like right if you got exactly 1/3, but you get close to 1/3 of the split. The bigger the number, the closest split you get. So that's how it works. Look how simple it is. And again, it's hard to appreciate the simplicity without a context, because I cannot show you other products and how it's done in other products. But I challenge you to find anything simpler than that, anything more elegant than this. That's how you collocate. That's a very complex operation, because keys can move. New nodes come up, old nodes crash. You add more data. Keys can eventually move from node to node. That's the only code you have to have. I feed you around, give me the name of the cache, what I'm dealing with, right? Give me the key, and give me the closure. By the way, this can be a sequence of closures, can be a sequence of keys too. We support a very, very deep API here. In simplistic case, give me the key, give me the closure. I'm going to find a way to put this closure on the node that has the value for this read. So the entire operations here is going to be local, and that's the key. That's the only reason you're doing an integration between a computer and a memory grid to collocate, because you want to have as much local execution on your grid as possible to minimize any data movement, remove any data movement unnecessary, remove any distribution as much as possible. Yes?
How much is the overhead when you store, let's say, 1 million ints or something like that? How much overhead is there for storing data?
It's an excellent question. We're actually working on it as we speak. We're trying to optimize that. The overhead can be significant because, for example, when you store just the 8 bytes, 4 bytes, right, that's what we typically. If you just wrap this in an object, how many bytes are we talking about? Probably 100 bytes right there. So this overhead can be quite significant if you just store ints. So we usually keep saying if you store just an int in a data grid, you have to think twice, because obviously, no matter what, it's not about GridGain. Any other product that wraps in an object or in a JSON will add up something overhead. Now, we're working right now to optimize our big memory support off-heap allocations. And that we can actually be a lot more effective, because when you do off-heap allocation, you basically do the memory allocations directly. And then we can be a lot more effective. So the next release, probably 4.3, maybe 4.4, a couple of months from now, we're not going to do anything about a heap size, heap size of Java. That's unfixable. I mean, there's some libraries like Trough, right, or Thrive, I don't know, Trough, I think, that actually do in-based, primitive-based maps and collections. But those have nothing to do with distributions. If you look at the distribution, you're practically out of the luck if you want to store very small primitive types. But when we deal with off-heap storage, which we support natively, and totally transparent to you, then we can optimize quite dramatically, because then we control. We don't have limitation of a heap Java management. We have basic full control of heap storage, and then we control. We're already doing it right now, but we're going to do it a lot better, and literally in about a month's time frame. So again, on the heap, you're always going to have an overhead, and the gap can be dramatic. It has nothing to do with GridGain. Any other product will have the same problem. With off-heap, we're going to have probably very limited overhead, I think. You can effectively store ints and longs and doubles or something like this in off-heap very effectively. Maybe 10% overhead. Literally, not really much to talk about.
Okay, that's for the next release, and in the current release, how much is it?
In the current release, I would say, there you go. The integers 4 bytes. If you wrap this in an object, which we do, you don't have about dozens of bytes. So overhead is quite dramatic. But again, you have to be careful, because most of the time you also wrap your integers and objects in your applications. So only if you store if you allocate a huge array of bytes, and then you're going to do a byte operations to store them, then it can be very effective. If you just work with the Java, ints, they get constantly boxed in and out of the Java language, right, and those objects. So you have to be careful. But yes, overhead is always there. And I would say there's nothing to do with GridGain, infinite span, coherence, data space. Anybody who is in and out of the space would have the same problem. And we start with it differently. We say, hey, yes, we're going to have overhead in one box. Once you spread it over, you basically you mitigate this problem. Mongo, for example, having a bigger, Mongo couch, anybody who does, document-based, they're going to have dramatically bigger overhead anyways. So, but again, it's not a indicative Mongo. It's, it's something that now those guys could solve. It's the nature of heap storage. In off-heap, again, you have a flexibility which we use. All right. What I want to show you, I want to show one thing, basically. Once we are there in a data grid, you can do something interesting. Let's go. Jesus.
Do you have any streaming?
We have a good example. Yes, we support actually a streaming MapReduce. I don't want to show you right now this, but we ship all our examples with the product. There's about 100 examples. You can obviously download it. It's free. Just look it up. And we support, for example, a very advanced feature of continuations. It's very cool stuff. It's basically, let me give you an example. Like 3 years ago, somebody asked us to create a Fibonacci example on the grid. And it's funny enough, you get this Fibonacci example, literally 5 lines of code, it crashes you immediately. Because you basically, Fibonacci is a string, right? It's a recursive string. So you basically, if you have like 5 nodes and you're trying to create a Fibonacci, it basically recursively splits tasks in the same node, in the same node, in the same node, and the node crashes. Because you don't release the resources, right? You create one task, it calls another task, it calls another task, while holding all the threads. So without continuations, you can never basically do that. So with continuations, and look at the example, I feel you guys are coming in. With continuations, you can actually resolve that very effectively. You can have recursive execution on the grid, and everything that sits on the stack will release the resources for you, but still can keep the continuous context, so you can always return back. So anyways, last thing I'm going to show very quickly, you can basically run SQL queries on, let's say, all the things, use a query, and just click, something like simple as this. Guys, you have to, yeah, we don't see, but you guys look at my laptop, you can see there's a data beneath there, but I cannot move this up. Anyways, full SQL, whatever you like to do here, like select start, wherever, from wherever, it's going to work perfectly fine. So I'm not advocating, because obviously it's a little bit awkward to use SQL to run, because we have full support for averages. But you can use any tools with us. Open your Toad, SQL viewer, see what's inside of memory. That's a perfect tool. Any kind of integration with BI tools, analytics, if that's your deal, you can do that. With that, thank you very much. Any questions? I'm here all day. Thank you.
Quick question.
Sure.
For off-heap allocations and interaction, what are you coding in C++ or what do you?
No, Java supports perfectly fine of heap allocations without safe. So that's what everybody uses. There's no rocket science here. The rocket science really is an algorithms. How do you, because unsafe gives you a malloc-free, essentially C operations to allocation memory.
Mm-hmm.
So you got to be very careful, because there is no, you have to provide your own memory management in how you effectively do this. That's the secret sauce, if you will. But the mechanics of that is trivial. But it's very important. Look, most of our boxes today have 64 gigs, right? How much GC can support? 4, 6, 8 gigs at most before you start getting huge GC boxes. So you allocate, let's say, 4 gigs in memory right for heap, and then you start managing the off heap, and that's how that's how you can utilize the 64 gigs of memory very effectively. And we do it. So that's how we support that. All right, whoever's next, sorry for overrun. But, I think I'm out.
No,